Night. This is problem 3. I still have to splice together the bastard that is problem 2, but here's problem 3. Hopefully this one will go a little bit better. So this is going to be the polar coordinates problem in the Newton's second law. There's lots of different variations that we could make on problems like this. So I really highly recommend when it comes to the polar coordinates, Newton's second law, that you try out some other problems besides this, but I didn't want to assign more than 3 homework problems. So let's take a look at the thing. It's got a contraption, and it's got this like slotted bar, and we know the velocity of it, 0.75 radians per second, and we know the theta double dot of it. Now, if this was rigid body motion, we might actually put a torque onto this piece, but we'll get that in the later part of the semester. So let's see, the dimension here is 0.6 meters. This thing is a little piece that's kind of like a little piston thing that's being moved up there. It's got 0.2 kilograms, right? So yeah, and then this angle is 30 degrees right there. So we want to determine the forces that are on this slider block. So here I've written out the problem, and let's get to it. Now, we need to do a bunch of kinematics first, and there's a bunch of geometry, not a bunch of geometry, but some geometry. We want to have the radius. We don't know the radius of this yet. So in order to get that, we know this length right here. So it's really the hypotenuse that we're trying to find. So we can find r. Well, we could write that r cosine of theta right here is going to be equal to L. So we can find r by taking L and dividing by the cosine of theta. So we take that L of 0.6 and divide by the cosine of 30 degrees. And we get, with our Hewlett-Packard calculator here, we get 0.6 enter and 30 cosine divide. We get 0.6928 meters. Is that right? I'll take 30 cosine times it. Yeah. Okay. So let's see, what else we need to do. We need to know, okay, so we have the angular velocity of this, but we really would like to get an r dot. Right, so because this thing is moving up this direction with an angular velocity, it will be moving, this point would be moving r times that theta dot, but it can only move upwards. So we kind of have to do a little geometry there, right? So it's almost like a coordinate transformation, but we don't need to go through the formal coordinate transformation. We know, like maybe I could just say that the we could find the velocity at the end of the thing. Let's see, the velocity in this direction also has to have a velocity in that direction right there. All right, so that the total velocity that one thing we want to find is coming up right there. Did I say that correctly? I think so. All right, so the velocity, let's see, I almost want to like pause it for a second. I don't want to state this the wrong way, so just a second. The notation here is that we could express this in a bunch of different ways. But we know that the actual velocity right here has to be coming up that direction. But there's going to be a component of it that would be going in that direction, which is, it's originating from the theta dot times r, right? So that distance, you know, I'll even put it onto here, onto the problem right there. This is r right in here. So we're going to have v, we're going to have like a, we'll call this the theta component, right? So v theta is going to be v, right, the actual velocity, which is coming right there, time, I think it's going to be the cosine of theta right there that we're going to measure, right? So if we were to do the angles right there, you know, we would have a velocity coming right there and a velocity that's coming up in that direction right there. And that angle is the same as this angle right there. And if you wanted to prove that to yourself, if if you rotate that right there, that would close this angle, and rotating this would also close this angle. So they got to be the same angle right in there. So we take this, and this is the hypotenuse because this is the actual value, so we want the component of it. Yeah, that would be true. And therefore that's going to be equal to r theta dot, right? So if we want to get the actual velocity of this piece right here, we would get this r theta dot divided by the cosine of theta, right? So that we're going to have 0.6928 times 0.75 divided by the cosine of 30 degrees. So and I did something wrong there, so I'll go 0.6928, there you go, and 0.75 times, and then 30 cosine of that divided. Yeah, and it gets really close. Ooh. I'm going to do that again. 0.6928, 0.75 times, and then 30 cosine divided. Yeah. Okay. So that ends up being 0.5. I get a lot of 9s, so it ends up actually coming out to 0.6. I think that's just a coincidence, right? So don't worry. Oh, 0.6, not 0.06. 0.6. And this is the meters per second. Okay, so now we want the r dot though of this, and the r dot now is really going to be equal to the VR, which is going to be V times the sine of theta, right? And that's going to be equal to r dot. So let me go down to the bottom here, below this, all the way down. So that's going to be 0.6000 times the sine of 30, right, which should be 0.5. So 30 sine, yep, times that. So we really just get 0.3000 meters per second, and that actually equals to the r dot. So that gives us part of what we want for our kinematics, for our polar coordinates. So we have r dot, we have theta dot, we have theta double dot. All we have left to do is get like an r double dot. So we do know that, like, if we're going to go for the theta component, the acceleration in the r component is going to be the total acceleration here, because it can only accelerate in one direction. It can only accelerate up and down. So this point right here, right, it's because it's changing onto there, is going to be the total acceleration times the sine, right? Because we're making like a little triangle right here, right? So this is the theta component of anything, and here's the r component of anything. But this has to be the actual velocity or the actual acceleration of the thing. So using that geometry is like the key to this. So now this is the total acceleration right here. We also know that the theta component is going to be this right here. And I said the theta component. Did I say that wrong? Let me think about this for a second. I think I just said this backwards. Yeah. This is going to be the theta component, and this is the r component. There you go. Yes. Because this is the radial component, and this is the angle right there that's in between them. We just said that it was the same angle as that. So this is the actual magnitude, and here is the theta component, and here is the r component. So put those into there. We also, let me think. think about this. Okay, so this one, we know that the A theta is also going to be equal to R times theta double dot plus 2 times R dot theta dot. And we know all of that, right? So we can actually get this at right here. Okay, so we get the radius 0.6928 times the theta double dot, which was given to us of 0.35, plus 2 times R dot, which we just found, 0.3000, and then theta dot, which is 0.75. Right, so we're actually able to get the A theta, 0.6928, 0.35 times. And then we have 0.3 and 2 times and 0.75 times. We can add those two together. So what we say is this is going to be 0.6925, and these are meters per second squared. Okay, so now knowing this, we're able to find the overall acceleration is going to be that A theta divided by the cosine of theta. So we get 0.6925 and divided by the cosine of 30. 30 cosine divide, and we get 0.7996 meters per second squared. So therefore, AR, this is what polar coordinates stuff like always does. AR is, as we said, it's going to be A times the sine of theta. So 0.7996 times the sine of 30. So it's just 1/2 of that, really. Right? 'Cause sine of 30 is 0.5. So we get 0.3998 meters per second squared. And we also can set that AR is going to be equal to R double dot minus 2, not 2, Jesus, I must be tired, you know, R theta dot squared, right? So we can say that R double dot is going to be that AR, which we just found, 0.3998 plus R, which is 0.6928, times theta dot, which was given of 0.75, and make it squared. So R double dot right there. And I don't even know if we actually need this unless it was asked for, but I don't think it was. I think once we actually got that AR, we were okay. And once we have this A theta, that's all we actually needed. So I think I'm doing this just to demonstrate. Yeah. 0.75 squared. Where'd you go, squared? There you go. Times. Ooh, it's going to be really. They're close to each other. This is actually 0.3897, and this is, alright, so add them together, and we get 0.7895. So if we cared about this, that would be something to know. But honestly, all we really need to do is just to find the forces that are acting onto this thing. So we just draw, well, let me make some room down here, and let me do the kinetics. FBD, IBD, and we can go, there is going to be my ER, and here's my E theta, and we're going to draw a little block just to represent something there. Doesn't need to. It's really just a particle, so we don't even actually need to draw like a real thing. Not really. But it doesn't hurt anything, I don't think. Alright, so here we go. Here's a... Okay, so we're going to have the side of this thing. Okay, so we got to decide which way. Maybe it's better to go ahead. I think we decided it had to be positive. Everything seems to have been positive so far. So we know that we'll put this as a dashed line right there. But that's really the acceleration direction of this thing. But we want to put it in terms of it's got a, I guess we'll try to make it look like a 30 degrees, something like that. So we're going to have an acceleration that's coming this way, and we're going to have an acceleration that's coming this way, right there, right? But we recognize that it's, I made these way too big, right? So it's coming up something like that. I think this one should look smaller. Well, that's a 7.895, and actually they get really close to each other. That's interesting. I wouldn't think that. I would think, because they're supposed to be, no, this one's 3.998, and that one, yeah, this is the one we're looking at, 3.9. So this one is shorter. That's right. So maybe, because the vector triangle should come out to like something close to that 30 degrees right here. So this is M-A-R, and this is M-A theta. That right there. Now the forces that are acting onto this piece. This is a little difficult to write down. Right. So first off, let's try to write this in as a dashed line, kind of through there, right there. So this guy can only be like this right here. So we can call this going to be F, and I think I'm going to go AO, right? That's because I'm naming that AO because, or maybe it should be OA because it's this bar right here. And then we got to get a name for this thing that's acting. It's either going to be from the left or it's going to be from the right. That's interesting. I think I'm going to choose it to go into the right onto this because I'm not quite sure. It's because this has a component that's going in that direction, so there must be something, right? The wall must be pushing back onto here. So I'm going to call this F, and what I decided to change my mind that I was going to make this OA instead of OA. And maybe I'll just call this F of the W. What did I call in the original problem? What did I say as the thing that's in here? Right. I said determine the forces on the side by both the slotted arm and the channel. I guess I'll call it channel. We'll call it channel. So the channel acting on this piece. So C. That's good enough. All right. And I think this angle, we got to be careful with this angle right here. What is this angle? I think this angle right here should be 30 degrees. I want to double check that. Like if we had like something like there and there, yeah, that's got to be 30 degrees. So I'm going to call this right here 30 degrees. So theta is right there. And that's mostly because I want to, but that's completely in that direction right here. So this guy right here, he's actually, I believe that too is theta right there, right? So let me double check on that. If that one moves, right? I think so. I think that's supposed to be theta right there. So what we could say is the sum of the forces. I think we want to go in the radial direction first. Sum of the forces in the radial direction equals mass times acceleration in the radial direction. And this is the positive radial direction right here. So there's none of this. This guy is completely in the theta direction. This guy has a component in the radial direction. So that's going to help us out, I think. Yeah. So we'll be able to find what his force is, because he does have some that's in the theta direction, but he has some that's in the radial direction, whereas this has none. So we'll be able to solve for that magnitude right there. So we're going to take FC, and that's going to be, yeah, we didn't do a good job of aligning that. That should be aligned with this right here. It's just like that should be aligned right there. So maybe we'll correct this just a minute, make it look a little better. There you go. Move this guy closer. ER. There you go. And so that's going to be the cosine of theta, and that's in the positive ER direction. And there's no other forces on this. Oh, wait a minute. It said it was in the vertical plane. Did it say in the vertical plane? It would be nice if it wasn't. In the vertical plane, you bastards is. Alright, well that's okay. We caught it. So this thing is going to have a mass times gravity. And you got to be careful with the angles here. Is this also going to be theta? Yeah, because if you close that up, do the same thing, close this up. Yeah, okay, so that's theta. So, and that's going to be in the negative. So we have mg, that's going to be the sine of theta. And it's going to equal MAR, which is just this full thing, right? We didn't need to find that, so we just need this guy. So we still can find FC from this. It's going to be the cosine of 30 degrees minus, and the mass of this is 0.2, 9.81 sine of 30. 30, not 30. It's like 10:06, I think. I'm tired. I still have to splice together that other video. Equals, oh, you ran out of room. Can you cram them in there? No. Do it anyway. 0.2 times 0.3998. Ugh. FC is therefore going to be, we'll take 0.2 times 0.3998, multiply them, and we'll take 0.2 9.81 times, but we'll take 30, take the sine of it, times, and that's going to move over to there, so we're going to add it, okay, and then we're going to take cosine of 30 and divide, and we get the force is 1.225 newtons acting onto the side. Now we take the sum. If I could cram it in here, I could get out of one piece of paper. Yeah, I know. I tell you not to do this. Square root, not the square root. What is that? What's even talking about? There you go. The sum of the forces is equal to mass times acceleration. Boom. And so now we got a lot of things to consider. We have, let's start with this one. This one has a negative, right? So there's going to be a negative FC times sine of theta. And then we're going to have a, is that true? This is also negative mg cosine of theta, because it has that part coming down, right? That's in the negative theta direction. And this guy's in the positive, plus FOA, and that's going to be equal to mass times acceleration. So we take negative 1.225 times the sine of 30 minus 0.2 times 9.81 times the cosine of 30 plus FOA is going to be equal to, got to go down to the next line point, and if I'm going to go down to the next line, I'll just stick it over to the side. 0.2 times up above this guy, 6925. Okay, so what we find is that FOA is going to be equal to I'll start over here. 0.2 times 0.6925. Enter. Alright. I didn't multiply, but there you go. Multiply. We got 0.2 times 9.81 and a cosine of 30. And that's going to come over and add over to there. So plus. And then we get this one. 1.225, but cosine of 30 times, and then that's going to come over plus. So I'm going to have a grand total of 2.450 newtons. Now, I really should use a new page, but I'm lazy. I'm tired. Answers. FOA is 2.45 newtons, and FC 1.23 newtons. And I'm a bad man for putting this in there. And maybe I should put the direction, the arrows on this, right? Because we are asked for the forces on the piece, so we know for sure what direction these forces are going to be. We might even want to try to like combine them together and make them an overall force onto the piece. But the way that the question was asked, you see, we want the forces on the slider box by both the slotted arm, which actually should be FC. No, that's the right one. OA and the channel. So this is the arm is the OA and the channel is the thing that it's in. I know this is not the most typical problem. There could be all kinds of other type of problems that we have in polar coordinates, and I only assigned you one. So I highly recommend that you practice solving other problems as part of your preparation for an exam 2, which is right around the corner, believe it or not. Even though we just had exam 1, they come quicker than you expect. So there you go, 28-minute video.